In this chapter, we're going to be talking a lot about the idea of congruence, specifically how this idea of congruence could be applied to shapes and figures. We've already discussed congruence in terms of segments, meaning that the segments have the same length if they're congruent. And we've also talked about angles that are congruent, meaning they have the same measure. Well, now we're going to apply that idea to figures. Specifically, we'll spend a lot of time talking about triangles that are congruent. So first we're going to just kind of, I guess, loosely, or we're going to define this idea of congruence of figures. So the first definition, the first thing I have for you on your note sheet here is a definition for congruent figures. And it would be figures that have the same size and the same shape. We call those figures congruent. Now, one way to determine whether or not figures have the same size and shape would be to think about the ideas that we just got done learning about when we were talking about transformations. Two figures would be considered congruent, the same size and shape, if we can use a rigid motion, if there is a rigid motion that maps one figure to the other. So for instance, if we look over here at this example diagram, we can see that we have these two triangles, triangle ABC here and triangle DEF here. And then we have a line here that would be a line of reflection. If we were to reflect this triangle across this line, then the vertex A would land on the vertex D right here. C would map to F and B would map to E. And since all those vertices on this triangle would map to a vertex on this triangle, we could see that those two triangles would have the same size and shape. And it's a rigid motion, and we already learned that rigid motions preserve angle measurements and side lengths. So the fact that we have angle A here congruent to angle D, that would make sense, because when this triangle gets reflected across the line and lands where triangle DEF is, we expect this angle to stay the same. Same with all these different side lengths. We expect segment AB and segment DE to have the same length because, after all, we used a rigid motion which preserves size and shape. So I have a question down here that says, why does it make sense that rigid motions are connected to the idea of congruence? Well, and this is what I was just talking about, that if congruence means the same size and shape, rigid motions preserve angle, measure, and segment length, and that's what gives a figure its size and shape. So if you wanted to jot down some kind of answer down there, kind of relating that idea that rigid motions, by preserving angle, measure, and segment length, they are producing images that are the same size and shape as the pre-image that we started with. One other note here that you're going to see sometimes, in this chapter we might use the word congruence, or the phrase congruence transformation, and that is just another name for a rigid motion, because a rigid motion maps a figure to a congruent figure. So sometimes we're going to call those, instead of rigid motions, we might use the phrase congruence transformations. So let's look at a quick example problem just kind of illustrating this idea of congruence transformations, or rigid motions mapping a shape to another congruent shape. It says, given that triangle XYZ is congruent to triangle ABC, meaning that they are the same size and shape, what composition of rigid motions could be used to map triangle XYZ to triangle ABC? In other words, how could we use translations, reflections, and rotations to move this one to here? That should be possible if it says that they're congruent. We should be able to find some combination of motions that would move this triangle to this one. So when I look at this, I notice that, well, first of all, if I look at this statement, it does tell me some information that I might not immediately realize. It's telling me, for instance, that point Z should go to point C, and it's telling me that because of the location within this triangle's name of the letter Z, and how it's in the same, the corresponding location to where C is in triangle ABC's name. They're both the third letter listed. And that tells me that they should map to each other. Same thing with X mapping to A and Y mapping to B. So now with that known, I know that I need to move z to where c is. I need to move x to where a is. I need to move y to where b is. Well, I'm going to start by just translating my shape to the right 3 units. So I'm going to start with a translation of, let's see, that would be a translation of 3, 0, because that's going to move z to right here. It's going to move y 3 units over, so now y prime would be here, so we'll call this z prime there. And then x prime would move over to this point right here. What's that? Negative 3, 2. So now I would have my triangle x prime, y prime, z prime that looks like this. And now my question is, well, how do I get x now to move to A and y to move to B? And some of you might be able to see this, but it looks to me like if I just rotated this around point C, or z prime, whichever you wanted to call this point right here, if I rotated this 180 degrees, the x prime would move around half a circle to where A is. The y prime would move around half a circle to where B is. So I could say, after I do my translation, I'm going to do a rotation of 180 degrees around point C. And that then should move y prime to here, and it should move x prime to here. Since z prime is already at point C, I know it's not going to move. That's one of the rules of rotations, that your center of rotation doesn't actually move. So that would take my triangle x prime, y prime, z prime to this new location here. So just to kind of write this out, I guess, in the correct notation, I would perhaps say I am going to first do my translation of 3, 0, and then I'm going to do the rotation to that. So of course this is the way I'm going to write that. It's a rotation by 180 degrees around point C of the translation by 3, 0 performed on triangle x, y, z that would map it to triangle ABC. So this would be kind of the rule for that composition of rigid motions that would do what I'm trying to do here. Now in this next example, it says, given these 3 triangles, triangle ABC, triangle EFG, and JKL, which triangles are congruent? So let's start by looking to see if we would be able to map triangle EFG over here to triangle ABC. And again, it would appear to me that E would need to match up to A, and F would need to match up to B, and G would need to match up to C. Now I think I can tell just by looking at this that this is not going to be possible. And the reason is, if there was a rigid motion that moves this to this triangle, then the segments should have to stay the same length. But if I look at the length of segment EF, that is pretty clearly 1, 2, 3, 4 units long. Segment EF is 4 units long. Let me just mark that on my picture. It is 4 units long. But segment AB is slightly longer than 4 units. And the way I can tell it's going to be slightly longer than 4 units is I can think about the distance formula that, or the way I view the distance formula, which is I'm going to kind of draw a right triangle using segment AB as its hypotenuse. And the length of segment AB would be this distance squared plus this distance squared, and then the square root of that. Right? So I'll kind of do that off to the side. The length of AB is going to be the square root of, and it looks like that's going to be 1, 2, 3, 4. So it's the square root of 4 squared plus 1 squared, and that 1 is coming from this segment right here, which is going to be the square root of 17. And the square root of 17 is slightly larger than 4. The square root of 17 on my calculator says it's about 4.12. But the length of segment EF is just 4. And so what that tells me is, since there's not going to be then a rigid motion that can move this to this triangle, because it would have to make segment EF get a little bit longer to match up to what segment AB is. So I'm going to say Therefore, triangle EFG is not congruent, so I do the congruent sign with a slash through it, is not congruent to triangle ABC. Again, I just saw that because the sides that should be the same length are not the same length. But now let's look at triangle LKJ or JKL. Can I get this one to match up to this one? Well, let's imagine translating this triangle so that A and J were in the same place. So I want to move A to where J is. So that means I need to move, let's see, over and then down. Looks to me like that's a movement over of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then down 3. And if I move all these points over 10 and down 3, so let me just write out what I'm doing here. I'm doing a translation of 10, comma, negative 3. That puts A right here, so we'll say A prime there. It puts B 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then down 1, 2, 3. It puts B right there at 2, comma 3. So 2, comma 3 would be B prime. And then C would be over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then down 3 would be right there at 5, comma 4. So that is where C prime ends up. So that translation moves my triangle to there. I'm going to real quickly get rid of this 4 right there, so that's not in the way. Okay, now I'm going to see if I can reflect this triangle to land on top of this one. And I notice that A is already where it needs to be. This point right here looks to be the midpoint between B prime and K. And this point right here looks to be the midpoint between C prime and L. So I think if I reflect it along this line right here, which is x equals 1, if I reflect it over x equals 1, A prime would stay where it's at, B prime would move to here where K is, and C prime would move to there where L is. So that triangle would land right on top of triangle JKL. So I did that translation, and then let me just write this out, and then I did a reflection across the line x equals 1. So I think that yes, I'll say yes, triangle ABC is congruent to triangle JKL because because the reflection across the line x equals 1 of the translation by 10, negative 3 performed on triangle ABC results in triangle JKL. So this is kind of the explanation of why these two triangles are congruent. I can do a congruence transformation, a composition of rigid motions that takes one triangle and maps it to the other, and that means they have to be congruent. Now we have one more example that's going to do kind of the same thing. So I'll move through this one maybe a little bit more quickly. First, it's asking if these two triangles, or not triangles now, I guess these are now pentagons, 5-sided shapes, if they're congruent. And they'd be congruent if I can move A to J, and then B would have to move to K, so B has to move to K, and C has to move to L, C has to move to L, and so on. So I look at this and I say, okay, if I move B to J, and then look at the distance between B and C and J and K, just like I mentioned in the example above, I noticed that B to C is only 3 units, but J to K is going to be slightly longer than 3 units. It would be the square root of, it looks like the square root of 10, because it would be the square root of 3 squared plus 1 squared, which would be the square root of 9 plus 1 is 10. So the length of JK is the square root of 10, but the length of BC is only 3, and those two numbers are not equal. So I know right here that no, not congruent, because the distance from J to K is not equal to the distance from B to C. Now the second question asks about triangle ABC and triangle WX, or not triangle, I keep saying triangle, pentagons. But anyway, these two shapes, are they congruent? Can I map this one to this one? Well, let's think about it. If I moved A to W, and then I would need to move A to V, B would have to move to W, C would have to move to X. Well, let's move by a translation. Let's see if we can put this one, let's just translate this pentagon over so it's directly above that. So I'm going to move it by just sliding A to directly above where V is. So A prime would be there, C prime, or E prime, I'm sorry, would be here, D prime would end up here, C prime would end up, I believe, right, nope, not there. Let's see, it wouldn't end up there. It would end up right here, and then B would be 3 units over from that. So there's C prime and there's B prime, and that looks to me like it's a translation. I'll count that in a second. So that is a translation by, looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the left. So that's a translation of -10, 0. And then can I just reflect this so that B ends up where W is, C ends up where X is, A ends up where V is? I think I can. I think if I now reflect it over the X-axis, right, if I reflect it over this X-axis right here, then B ends up right here. We'll call it B prime prime. C prime prime would be there. This would be D prime prime. This would be E prime prime. And this would be A prime prime. So we can see that pentagon ends up being right on top of the other one. So followed by a reflection across the X-axis. So my answer will be yes, there is a composition of rigid motions that maps the pentagon ABCDE to this pentagon. And let's just go ahead and say it. Yes. See, a reflection across the X-axis of the translation -10, 0 of ABCDE results in VWXYZ. And there we have it.